Well, in the last video, we talked about how we can find the potential due to a dipole, which is basically just a positive charge and the negative charge, which is of the same magnitude, just placed apart at a distance d. And we discussed how we can find the potential due to these two charges, or as we call them together as a dipole, at a point P, which is at a distance r from the center of the line joining the two charges, and at an angle of theta, which I forgot to mention in the last video. Anyway, so in this video we're going to try to find the magnitude of the electric field at this point instead of the potential, which we did in the last video. So yeah, let's get started. So the one thing you can notice in these circumstances is the electric field is not going to be, just a standard kind of thing, because it's not going to be like along this line or perpendicular to this line. It's going to be somewhere in the middle of those two, and we can see that because we can just vectorially add the fields due to these two charges, right? That's essentially what we're doing. So the field due to this charge, the plus q at point P will be around somewhere like that, and the similar electric field due to the negative charge at the point P will be somewhere like that. Not quite, but yeah, you get the point. So you can see that to get the final electric field, we just add them vectorially. So it'll look something like this, and let me just, yeah, it'll look something like that. See, so it's not like it's perpendicular to that line, though it looks like perpendicular, but it's not. So we need to find a better, a better way to find it. So instead of finding the magnitude directly, what we're going to do is find two electric fields whose summation will give us the net electric field at point P. And what I mean by that is whatever electric field might be there, let's suppose it's right there, it can be broken up into two components of along this line and perpendicular to this line, right? That's what we do in vectors. When you write a vector named phi I cap plus 2j cap, that's essentially the addition of two vectors, which is 5 in the horizontal direction, 5 a vector of magnitude 5 in the horizontal direction, and you add that to 2 I cap, which is 2j cap, sorry, which is essentially a vector of magnitude 2 in the vertical direction, and the addition of those two vectors will result in this vector, which we write as phi I cap plus 2j cap. So you see that it's simply the addition of two vectors which are perpendicular to each other. So that's the same thing we can do right here, right? So I can break that up into two components, whatever the electric field is, I don't care. So it's going to be broken up into two components right there, and let me name this component as E, let's say R, because it's along R, you see. And let me call this one E perpendicular, I guess. Okay, let me call that E theta just for fun. Okay, so essentially what we can do is we can easily find ER and E theta, right? Because they're kind of perpendicular and along, so it's kind of easy to find. And then we can just vectorially add them and find that magnitude, and that will give us the final electric field's magnitude right there at point P. So how do we find ER and E theta? So to do that, we'll use one of the definitions of potentials, which I must have discussed, and I'm sorry if I have not, but I'll just mention that right here. Electric field is simply dV over dr. I might have written that somewhere, but let me write L instead. I might have not explained what it is. So essentially what it means is, if I want to find, let's say, let's consider a case here. This is some space in the universe, I don't care what it is. So let's suppose a potential is defined everywhere in this space, and that potential is defined as a function of position, which I'll write as r. So V of r is the potential at any point in the space with origin being somewhere, I don't care. So if I want to find the electric field in this direction right here, what I'll do is I'll find the, let's suppose origin is here, right? So what I'll do is I'll find the potential difference between this point and this point. So it's essentially the change in potential. So I'll write that as delta V, and I divide that by the, you know, the displacement between these 2 points. So if that is, let's say, r, no, not that would be r, let it be L, let it be L. Okay, so if it is L, then I divide that by L, divide delta V by L, and I get the electric field at that point. And you can see that it's not quite well defined. So to define that at one point, we just we tend L to 0, by which we mean that we shorten the distance to approximately 0, not quite 0. So that will give us the exact electric field at that point. So electric field at that point will be, now if L is tending to 0, you can see that delta V will also tend to 0. I mean, it's kind of correlated. So instead of delta V, I'll write dV. So that is the change in potential there, and I divide that by L, but L is, as I said, is tending to 0, so I'll replace that by dL. So you see that this is the definition of the electric field. So anyway, that was kind of a side thing. So we'll just get back to the problem here. So as I said, it's just dV over dL. So if I want to find the electric field in this direction, that is along the R, then you must know that, as I said in this side note right here, you can use that to tell that the electric field R, by which I mean that this electric field here, that electric field will be dV over dr, right? Because we're traveling along R, so if this vector is R vector, denoted like that, then the change in the displacement here will be dr, right? And we tend that to 0, so we get the dV over dr. So and usually this is kind of mathematical, but turns out that you can also replace the d with a partial derivative. So it's the partial derivative of v with respect to r. If there are any other terms, you can neglect that. Means if there is theta, then then there is no need to differentiate that. That's what essentially it means. So E at r will be partial derivative of v with respect to r, but we already know v, right? It is this kp cos theta over r square, which we derived in the last video. So we'll just differentiate that with respect to r, and partially, note that it's partial, so we can just bring out the theta term. We don't need that at all because we're partially differentiating. If it was the simple derivative, then we'll also introduce d theta over dr, but since it's partial, there's no need to do that. So it's simply the partial derivative with respect to r of v, right? V is kp cos theta over r square, kp cos theta over r square. So if you can do it right, then kp cos theta will totally come out because it has nothing to do with r. So it's kp cos theta times the partial derivative of 1 over r square. But now 1 over r square, you can easily differentiate that. 1 over r square is simply r to the negative 2, and if you differentiate that, you'll get minus 2 times r to the minus 3, which is essentially minus 2 over r cube, right? So it's simply er. Let me change the color here. Let's use white. Er is simply 2 kp cos theta over r cube, and there's of course a negative sign, but yeah, that's my mistake because I forgot the main part here. There's a negative here. I'm really sorry about this. I just forgot that. So there's going to be one more negative here, so that'll cancel out with the negative 2 here, and I'm really sorry about that. It's E is the negative of the differentiation of V with respect to whatever displacement you're trying to find out. So we've got ER. Now we'll find out E theta, and we are essentially done, because then we just factorially add them to get the magnitude of the field. So to find E theta, well, we're moving in this direction, right? And what is that direction? There's not quite uh, a vector that represents that direction, but if you notice carefully, there is, because let me draw this down here, just a small part of it. So it was something like that, right? And there was point P, and this angle was theta. This angle was theta, and this length was r, right? So if you move in this direction, which is perpendicular to um, this blue line here, and if that displacement is small enough, then if we join the origin with that point right there, then this essentially will turn out to be an arc of a circle. Well, not quite, if that length is that displacement is quite big, but as I said, it's all in differentials, right? dr, dl, so it's very, very small, so we can approximate this as an arc of a circle. So what is this length here? Well, if we take this angle, small angle, obviously, as a small theta, which we write as d theta, then if you know your geometry, then if there is an arc of circle and this angle is, let's say, alpha, and this radius is r, then this circumference, not quite the circumference, but a part of a circumference, or as we call it, the arc of a circle, that length is r alpha, right? So similarly in this case, we'll do that. So it'll turn out to be what? R times d theta, right? So that's r, oops, so that is r d theta, right? And yeah, that's pretty much it. So we'll just calculate that. So at E theta will be dv, well, not quite dv, it's partial v, yes, and we divide that by the displacement, right? And the displacement in this case is r d theta, so that'll be r d, well, not quite d again, it's partial d theta. So that'll be what, 1 over r times the partial derivative of v with respect to theta, and that'll give us 1 over r times the partial derivative with respect to theta of v, which is again kp cos theta over r square, right here, kp cos theta over r square, kp cos theta over r square. And in this case, everything that is not related to theta will come out, right? So r is not not related to theta, kp is not related to theta, only the cosine term here is related to theta. So we'll just differentiate that, and the rest everything that is kp over r square will just come out. And if we take that out, then there's a 1 over r here, so that'll be r, it'll turn to r cube, right? So it'll be kp over r cube times the partial derivative with respect to theta of cos theta. Well, the derivative of cos theta is again sine theta. Well, not quite sine, right? It's negative, and I did the same mistake again. Such an idiot. It's again, this is negative, this is negative, this is also negative, and that negative will eat up, the derivative of cos theta is minus sine theta, but there's already a minus, that will eat up, and yeah, that's pretty much it. So we have found E theta as well. It's kp sine theta over r cube. So there we have it. That's E theta for you. And we also have ER. So to find the net electric field at that point, the point P, it's essentially the vector addition of these two, right? It'll be something like that. And to find the magnitude of that, it's just Pythagoras theorem, right? It'll be let's say the magnitude of electric field at the point P is EP. Then by Pythagoras theorem, EP will be the square root of ER square plus E theta square, right? You can see that here. Yeah, there. So this magnitude will be ER, right? It's kind of a rectangle, so it's ER as well. So this length squared plus this length squared is this length squared. So I just take the square root of both sides to get what I want. So EP is root of ER squared plus E theta squared, and it'll get quite quite long, so I won't do that in this video, but you should get that quite easily for yourself. And yeah, there we have it. And in the next video well, we have completed the dipole part, so we'll turn to capacitors now. And yeah, I'll see you in the next video.